Hi everyone, so today we're going to solve this problem 785 on leetcode is the graph bipartite. So there's an undirected graph with n nodes, and each node is numerated between 0 mm, and n minus 1. And we are given a 2D array graph where graph U is an array of nodes that's node U is adjacent to. More formally, for each node, for each V is graph U, there is an undirected edge between U and V. So the graph has the following properties. There are no self edges, there are no parallel edges. If V is graph U, then U is in graph V, so it's indirected basically. The graph may not be connected, meaning so there might be two nodes such that there's no path in between them. And a graph is bipartite if the nodes can be partitioned into two dependent sets A and B, such that every edge in the graph connects to A and in set A and a node in set B. So just to make it more clear, basically this is a bipartite, means that I can group these two unconnected. So let's see. Um, okay, so here, if we have a bipartite graph, is if we have like 1, 2, or 1. These are the nodes 1, 2, and 3, 4, 5. I can group them in two different groups, and let's say these are connected. These can be connected, but so we can have two groups A and B, that A and B are connected. However, the nodes inside each group, they are not connected, so there's no edge like this or this. This is a bipartite graph, but if we have something like this, there is no way that we can separate these two. So we want the answer false for this, and here if we are given this graph, the answer is true. And so our answer is true and false, and the input is a 2D array, like so. So for example, we start from index 0. So let's say this is 0, 1, 2, 0, 1, 2, 3, 4. So the input is a 2D graph like this. So node 0 is the first index. We write its neighbors. It's 1 and 2. Node 1 has 0 and 3. Node 2, 0 and 3 again. node 3 has 1, 2, 4, and so on. For node 5, for node 4, we have only 3. So as you can see, if these are the indexes, so we have 0, 1, 2, 3, 4, or indexes are actual nodes. All right, enough with the question. So let's go look for a solution. So the first thing that you can, it's obvious to solve this problem. We are going to use a BFS, Birdford search algorithm, to color the graph. So this is a graph coloring. We can say graph coloring. So we color. We start from this, let's say, a starting point, and then all of we color the neighbors of this node with another color, let's say red here, and then we go to process the neighbors, and we choose again the same color. So neighbors of this is going to be, and uh, like green, and again neighbors of this is the same node, and then we switch the colors between green and red, let's say, and we do this for I think we need to do it for each node. So let's go to the code, or let's actually have another example, which, let's say, an easy example that it's not possible to color the graph. So I'm gonna clear this board and start fresh. Let's say this is my node, or this is my graph. We start with color blue. We color this blue. Each neighbors we color it red and red. So this is where we start to, this is our source, and then we use a queue for BFS, right? So at first we have the source, then we have, let's say if this is 0, 1, 2, we put 1 and 2 into the queue, and then we process the next one and remove it from the queue. So now the current node to be processed is 1, and we check all the neighbors. If the neighbor is already colored with the same color, we return false, which is this case, in this case. And yeah, that's pretty much it. So another example, a more complicated example maybe. Let's say this graph. The graph may be disconnected. So I want to have an example with a disconnected graph, and yeah, let's say 0, 1, 2, 3. Start from 0 and color it blue. Oh, and I forgot the edges. And color, so put the neighbors into the queue, the first neighbor, then the only neighbor is this, and then next we process this. And so we have to do it for each loop because the graph is disconnected, and check, do a BFS on every node. So the next round we do a BFS on this, next round we do a BFS on this, and finally we do a BFS on, until we get it true. Until we get true. If we don't, if we navigate, if we iterate over all the nodes and we don't get a true output, that means the graph is not bipartite. So let's go back to the code. And let's start writing a code for it. This is going to be this is a medium question. I think it's can be even easy. All right, so for BFS, we'll write a new function, and we set this as the input or constant input, call it graph G, and then we have a source, which is the source node to start the BFS. And we will have a queue, call it queue push source while the queue is not empty. We get the current node to be processed and pop the queue, or yeah, pop. Now gets interesting. So we're gonna have a color for each node. We need to store this color somewhere. Usually in a BFS we use a visited array or hash map. We're going to do the same thing here. We're going to use an unordered map here of integer to int, or we color map. So this is the node to color. Okay. So the first things, and we need to define the current color. We start with number 1. So let's say 1 is blue, -1 is red, and 0 is uncolored, or yeah, transparent maybe. That's why we're using the current color. So when we push, so let me move this to the top. When we push this, we need to check the color map. If the current node is uncolored, first we okay, if it's uncolored, actually, yeah, here after we push this, I guess it's better if we do this. Okay, and for each neighbors of this, for each neighbor of this, if the color map of the neighbor is equal to the current color, so this is then return false, and we are done. Otherwise, color map of this is equal to minus color, and q that push neighbor. Yeah. At the end, we can return true. And here for integer node equal to 0, always less than graph size, if BFS of graph and node turn true, turn false. Now let's see if we let's see how to debug this basically. So I will need to, yeah, let's open some space here, and so we have our queue here. Right now it's empty. You have color, and you have the current node, and let's say we're working on the example 1 here. So first put 0 and then a color map. So we put 0, this is the color map, to 1. We insert this here, and the current color is 1, and then we start. The current is, we pop from the we get the queue front, and pop from the queue. So the current node is 0. So for each, and this is our graph here. Or G, and just to make it easier, this is our indexes. So for all the neighbors is 1, 2, 3. We color 1, 2, 3. So 1 with -1 because it says minus color, and 2 -1, 3 -1, and this all goes to the queue. Because the color of this initially is 0 because it doesn't exist in color map, so we will go inside of the for loop. At the end, I think we need to reverse the color. The current color. Let's see if we don't do this, what happens. The next round, we get 1 from the queue, and for each neighbor of 1, which is 0 and 2. If 0, color of 0 is 1 here. So for the neighbors 0 and 2, 0 is 1. Is 1 equal to 1? Yeah, so we'll return false. We don't want to do that, so we need this. So current color is -1 now. Color of 0 is 1. Is 1 equal to -1? No. So we color. Okay. So we negate and we change the color here, which is again another bug. Color map. Sorry, what is the current node is 1. Yeah, it's 1, and the current neighbor is 0. So okay, we don't want to do this because we don't want to change the node that is already colored. So and or first we check if color map of has this. Yes. And the color is equal to that. Yes, return false. Otherwise so what if the color map of the neighbor What if we go to this, but this condition is not false, it's not true? So let's see an example. What if I go to this is neighbor 0, color of 0 is 1. Is 1 equal to -1? No. So we continue with it. We don't do anything. We check the next neighbor. 2 is -1. So is -1 equal to -1? Yes. So this is false. This will return false. Now let's try this example and reset everything. So 0 to 1, and the Q will include 0. Color is 1, so the current node is 0. We remove it from the queue. Neighbors of 0 is 1. The first neighbor is 1. And we say, is 1 in the color map? No. So we do this. We do the opposite color. We color it with the opposite color. And we push it to the queue. Next neighbor. Is 3 in the color map? No. So push it to the queue. Now we change the color to -1. Now we pop from the queue, and the first neighbor of 1 is 0. Is 0 in the color map? Yes. Is the color of 0 equal to current color? No. Continue. Next neighbor. Is 2 in the map? No. Put it there with different color. And yeah, we put 2, and we are done here. So now the current node is 3. Pop from the queue. Add queue 2 to the queue. Next node is 3. Is 3 in 3 the first neighbor? 1 is not equal, move on. 2 is not equal, move on. So we are good. And then put the last node is 2. Is 2 neighbors of 2 is 1 first of all. 1. Oh, and the color is 1. Is -1 is not equal to 1, so continue. And -1 is not equal to 1 again, so continue, and then we return true, so this will return true. So I think we are good. Let's run it one time to see if there are any compile errors. There's none. And run all the example cases. Okay, we have a bug here. So the second test case failed. Second test case failed. Let's run it here to make sure if this is the one that is failing. Okay, so this is the second test case. We're gonna need a whiteboard to debug this. Okay, I'm gonna switch to whiteboard or blackboard, and we're gonna debug this and find the bug. This is the algorithm. I want to have it here and make it smaller maybe. Don't know if I can make it smaller, or I can, yeah. And this is my graph. This is our graph. Zero, 1, 2, 3. Okay. And we have this queue, and color, and current, and neighbor, and color map. First we start from here. This is our source. Current color is 1 is blue. And okay, much better. So we color first. We color this 0. Color map would be 1. And while the queue is not, and this is set to queue, while the queue is not empty, pop from the queue and set this as current. All the neighbors are 1 and 3. First we process 1 and we say if the color map has 1, no, just put it there with the different color, and put it into the queue, push it to the queue basically. This is number 1. Again, number 3, is 3 there? No, put it there. Push it to the queue. And reverse the color. Now the color is -1, which is red. Okay. We have current one is now, yeah, it's 1. Neighbors of 1 are 0 and 2. First, process 0. Is 0 in this map? Yes. Is 0 have the same color as the current color? No. Move on. The next node is 2, or the next neighbor. Is 2 in this map? No, so we go to the else, push it to this, with this color, which is blue. So far so good. And we just put 2 into the queue right now. And we reverse or flip the colors to red now, whatever that was. Oh, it was red. Now it's gonna be blue. Okay. Okay, moving on. Next guy in the queue is 2. Neighbors of 2 are 1 and 3. Is 1 in the color map? Yes. Does it have the same color? No. Move on to the next, which is 3. The next neighbor is 3. Is 3 in here? Oh, wait a second. We already colored this. Yes, it is in this. And is it in the same? Yes. So return true. So this will return true. This seems correct to me, but I will find what the issue is again. I'm going to put this breakpoint here and debug. The current color is one. Okay, 1. Let's continue. Current is 3. Okay. Color map 3. -1, -1, 1. 0, 2 is 1. Wait a second. What was that? It was 3. No, I'm gonna need to do it one more time. think I need to do this. Oh, I see it. We didn't color it here. Hmm, no. Okay. Okay, found the bug here. Uh, so basically the issue is in this line of code. This need to change this to color map of current. And yeah, that's the bug. Found the bug, and the uh, time complexity of this is we go off nodes plus edges and the space. We're using a queue here. There's no we go off n worst case. And yes, that's it for this video, and I hope you liked it, and I'll see you in the next video.